All right, so today I'm going to talk about understanding the unformatted trace and diagnostic data packet encapsulation for RISC-V specification. Now, it's a bit of a mouthful, and we'll come to why that's such a long title in a minute. So this is basically a summary of what I'm going to cover today. So we'll start with some historical background. And hopefully it'll become a bit clearer why the title of the specification is such a mouthful. And then we'll dive into some of the technical details. We'll look at the overall structure. I'll give some transport examples and then summarize at the end. So, so the background really is that, so this all started with the efficient trace for RISC-V or E-trace standard. So that work started way back in 2018 when Ultrasoc developed the first commercially available trace encoder for RISC-V. That essentially became the basis of the E-trace specification, which was initially ratified with instruction trace only support in 2020, and then data trace was added in 2022. But that specification only defines the payloads of the trace packets, doesn't deal with encapsulation. Encapsulation there were some informative examples of how you could encapsulate the trace, but they were informative only, and it's become clear more recently that that really needs to be standardized. And so in June 2023, we set up the E-trace encapsulation task group, and in just over 1 year, that turned into a ratified specification, which is the Unformatted trace and diagnostic data packet encapsulation for RISC-V specification. So so let's look at that in a little bit more detail. So why the long title? As I say, it was driven by the E-trace spec and the fact that it didn't define the encapsulation. However, the resulting specification is suitable for any kind of unformatted diagnostic data and not just E-trace. So yeah, E-trace packets, sure, but also performance counter metrics, logic analyzer trace, any number of other forms of diagnostic data. Not N-trace packets, which are already formatted. So this is where the unformatted part in the name comes from. So they already use a 2-bit code in every single byte, which is used for the formatting. So it's kind of distributed encapsulation, if you like. So hence the unformatted part in the name. And it can be used in conjunction with a whole variety of different transport mechanisms, so it's suitable for use with AMBA ATB, or the messaging infrastructure, which is used by all the embedded analytics IP from Siemens. So, so about the overall, let's go into the overall structure here a little bit. So the what we call the normal encapsulation is I guess the main bulk of what this is about, and that comprises a header, which is a single byte, a source ID, so this tells you where the trace came from, and that can be anywhere from 0 to 16 bytes. So 0 means it could be missing, it could be omitted completely, and that size is fixed for the system. So much the same way that in a memory map system, you have some number of address bits, and the number of bits you need depends on how big your memory is. So depending on how big your system is, how many trace sources you have will determine how many bits you need for the source ID. Then you have a timestamp. So this can be some number of bytes, up to 8, and that is included or not on a per packet basis. And then you have the payload itself, which is somewhere between 1 and 31 bytes. So you end up with these two basic structures here, where one with a timestamp and one without. So this is in network order. So the least significant bit of the header gets transmitted first if this was over a serial interface, and then the final bit of the payload goes last. There's also a null encapsulation. So this is used for synchronization, or when there's no data to send, if you need to do that. And I'll cover that a little bit more later on. So if we dig down a bit deeper still, so this is what the header looks like. So it's a byte, and it comprises 3 fields. So the first one, first one is the length field. So there's a 5-bit value. This is where the length between 1 and 31 is recorded. There's then what's called a flow field, which is used for routing packets to a particular trace sink. So you can dynamically route different packets from different sources to different endpoints. And then finally, there's what's called an extend bit. This is the bit which determines whether there's a timestamp or not in the packet. So if this is 1, then there will be a timestamp. If it's 0, there won't. And then the payload itself is further subdivided into 2, I guess, subfields. So there's first of all, there's the type field, which may be 0 bits in length. So if your trace source can generate more than one type of trace data, then this is how you distinguish those. And so, for example, in the eTrace case, this is used to distinguish the instruction trace and the data trace packets. And then this part is where the payload, which again in the eTrace case is defined in the eTrace spec. This is where the payload goes. So this is the basic payload structure. Then, so the packet length, I mentioned there's a length field in the packet. So all the packets after encapsulation are a whole number of bytes in length. And so the total length is based on this expression here. Right? So we have a 1, that's the length of the header. S is the number of whole bytes in the source ID. This is the number of bytes of timestamp, and this is the actual payload length from the header. So this tells you how long the entire encapsulated packet is. But you may remember from a couple of slides ago, I said the source ID could be any number between 0 and 16 bits in length. So it doesn't have to be a byte. And so what happens in that case? Well, so what happens? This is why this is a number of whole bytes. So for example, let's suppose that the source ID was only 3 bits long, right? So in this case, this would be 0. But you've got 3 bits left over that you have to account for somewhere when you assemble the length of the whole packet. So what happens is you take the length in bits of this trace payload, you add on the number of bits of source ID that weren't accounted for here, and then you work out how many bytes that is, and then that's the value that goes in here. So effectively you can kind of, if you like, borrow some bits from the payload length in order to account for any odd bits of the source ID. And this means you're not mandated to have source IDs which are bigger than you need, so that you can get the most efficient bandwidth utilization out of your trace infrastructure. There's more details on how this is worked out if you look in the specification itself. Okay, so then I mentioned the null packets earlier on. So generally, if you're transporting trace on chip, there will be usually some kind of sideband signal to indicate whether the data on the bus is valid or not. And so you don't have to worry about when there's nothing to send. When you've got nothing to send, the valid signal goes low. But when it comes to transporting that data off chip, over some form of in-band signaling, maybe it's just a serial link or a SerDes, or you need some means to be able to send, indicate that there's no data being sent. And a null packet is used to do that. It's also used for synchronization purposes. So again, if you were sending stuff over just a data stream, you need a way to identify where the packet boundaries are. You need a way, if it's a serial link, to identify where the byte boundaries are as well. And so the null packets can be used for that purpose. So within a normal trace packet, you can have up to 31 bytes of payload. Of course, that payload could all be zeros, right? Actually, I should say the null packet is usually what we call null.idle, which is a single byte with a value of 0, right? But obviously, you can have a 0 value in a payload of a normal packet. In fact, you could have up to 31. And even if you had a timestamp, the timestamp could be 0, and if the source ID could be 0. So somewhere, depending on exactly how long your timestamp and source ID is, somewhere in the region of at least 31 bytes of zeros is the maximum number of bytes of zeros you could have inside a packet. Right? If you see more than that, then you must be outside a packet in an idle region. And then the first non-zero byte you see after that will therefore be the beginning of a packet. And if it's a serial protocol where the data, where you don't know where the byte boundaries are, then there's also a null.alignment packet, which is another single byte. This time the MSB is a 1. And in this case, that's used to terminate the idle sequence. And that means then the first bit after this 1 is the beginning of a packet. All right? So you don't need to send that at all if the data is going over a data stream which is already composed of bytes, or if that data is in turn being encapsulated by something else like USB or the MIPI trace wrapper protocol. You don't need to have the additional, you don't need to be able to identify the byte boundaries. But it gives you the flexibility to do all of those things. Okay, so a few transport examples. So if you were to take these packets and you wanted to transport them over ATB, for example, so ATB has a sideband bus called, or sideband signal called ATID. So and that's where the source ID of the packet would be transmitted. So you don't need to include it inside the packet itself. So in that case, you would use basically the source ID would be 0, and so you use these 2 formats here. In the case of ATB, the flow field in the header is not used because there's no concept in ATB of routing packets to being able to dynamically choose the endpoint. They all go to somewhere which has been statically set up beforehand. And then another example, so if it would be the messaging infrastructure used by the Siemens embedded analytics IP. And in this case, there are no sideband signals, just valid and ready in data. So all of the packet contents have to be in band. And so in this case, the source ID would be included here in the packet. And in this case, the flow field is used to route packets to so you can have multiple different trace syncs active in the system. You might be sending some things to an external interface. Other things go to might be going to an on-chip RAM, and they could be transported over the same infrastructure. And so that allows you to do that. And I guess just to reiterate the initial point that this is not just about trace. So this encapsulation is something which actually Siemens has been using for a long time. This is, I guess, a slightly more generalized form of the approach that Siemens have been using for a long time, and Ultrasoc before that. And so this encapsulation format is used for many types of trace. So processor trace, bus monitor performance metrics and trace, logic analyzer information, code profiling, instrumentation, DMA data, and so on. There are many sorts. It's also used for configuring the IP. So we actually use this infrastructure in both directions, as well as getting trace data out. Configuration data goes in over the same network, and so we use the same basic formats for that. So, in summary, what we have in the unformatted trace and diagnostic data encapsulation is simple, it's flexible, it's very general purpose, it's transport layer agnostic, and also suitable for eTrace. And that's so thank you very much. And I have a few minutes for questions if there are any.
And I've got a microphone. Okay.
Robert wants a microphone. Hang on, wait for the microphone, Robert.
I'm hustling. There you go.
Yeah, question about ATB, because you skip the source for ATB. It means you have one ATB input per source, kind of?
Didn't skip the source. I left it out because the source information for ATB is transported over the ATID signals.
Yeah, I know. So it means you must have one ATB ID per a source, right?
Yes, that's exactly. Yeah. So so the source ID. So the source ID information is still there, but it's not in band inside the packet. It's sideband on
right on the ATB bus. Okay.
Yes.
Because that's kind of different than what say ATB sync in the control panel has, because it has you can packetize the packets and then you can attach one ID ATB ID to a sequence of packets, whatever group, right?
So this is an example. You could do that as well, right? You could have a source ID in the packet and a separate ATID. There's nothing to stop you doing that. So this is just an example of how you could, in a simple case, you could send over ATB without.
Thank you.
Yeah.
Okay, we had another question. Yeah.
In that slide, you show some packets with a timestamp with some without. So if you send one with a timestamp and then a number of packets without a timestamp, have they all happened at the same time?
No, it's so that again, I guess this would depend on the particular source, but in certainly and how that source was programmed to function, right? So that could be one example. You might have multiple packets at the same time, and so there's no need to send a timestamp with the subsequent ones. But also, depending on your use case, you might not be interested in time. You just turn it off, right? You may not care about when that data was generated in the context of the system, and so turn it off and save the bandwidth. So there are a number of ways that you could configure that, but that's nothing to do with encapsulation protocol. That's entirely down to the whatever diagnostic instrument is generating whatever kind of trace it is that you're transporting.
You got any time left?
I have 1 minute 45 left, Bill.
Any other questions? Yep. All right, I'm going to flip by here.
Bruce.
Yeah, requiring the length in the header, doesn't that put burden on the hardware to have to know the size of every packet before it can create the packet?
Yes, it does, but it also gives the hardware the capability to maximally compress that packet. So if you've got upper bits in the payload which are all the same value, for example, whether that be all ones or all zeros, you can compress those away without regard to what the structure of the packet is. You don't have to know where the different field boundaries are within that. You can just compress down as many bits as possible and adjust the length accordingly. Right? The recipient software that's receiving that's receiving or decoding the packets will know where they came from, and it will know what the full size structure looks like. So if it's expecting a packet which is defined to have 150 bits, and it only gets 10 bits, it just knows to take let's say bytes, right, rather than bits. It gets 5 bytes, and it's expecting 16 bytes, which just takes the most significant bit of the 5th byte and just sign extends it, and that will reconstruct the original. And you don't need to know about the detailed breakdown of the payload's contents in order to do that kind of compression.
Okay.
All right, I think that's it.
All right, yeah, it is exactly
Okay.
time. Thank you.